Hello, my name is Taha and I worked on Matlab and software.
Hi, my name is Eric Nordland. I worked on Matlab and videography.
I'm Matt, and I focused on the hardware.
My name's Joe. I worked on the reference documentation and various troubleshooting.
In this project, we are using a voltage divider in Arduino using Matlab to display raw and calibrated data for a thermistor. We are also displaying the resistance of an attached photocell. Both of these data sets are displayed in real time on a single graph. The thermistor graph displays the temperature based on a linear approximation, temperature based on a sine hot model, a running average, a thermistor resistance, and finally the difference between the two temperatures.
So for our hardware, it was pretty simple. We were able to use an Arduino and use a voltage divider on a breadboard to read the voltage and the resistance in to the analog pins in the Arduino. We started with a reference document here that was provided by Schumann, and I will try to color it so that it's got the same coloring as the ribbon cable up here. So for our photocell, we started with blue for the power. And then green is our analog read. Sorry for these terrible lines. And yellow is the ground. And for the thermistor side, we have purple as the VCC. We have got gray as its analog. And we've got white for its ground. Oops, a little too far down there. And with this, we were able to create a simple voltage divider inside of Matlab with the code and read in the resistance values of both the thermistor and the photocell.
So for the Matlab code, we've decided to use animated lines on our figures so that we can have a live graph of the data as well as some labels that show live data just at an instant of time. So we have the Steinhart model, animated line, and then the linear model, and then the running average, animated line. And then here are some things where we just add a label for the x-axis and set the bounds for the y-axis and a label for the y-axis and then the legend. And then we have the labels for the live values. So at the top of the graph, we have the thermistor R value. We have the percent error between the two models, the linear and the Steinhart model. And then we have the photocell R value as well at the top. So then we have an initializer just of the current time as a reference for the x-axis values. And then we have this loop here which goes through plotting basically every point on the graph for the lines. So we start off by reading the voltage values from the Arduino, and then we calculate the R values based on the voltage dividers that we've built here. Then we update the labels at the top that show the thermistor and photocell R values. So then after the R values at the top of the graph, we do the Steinhart model calculation, first in Kelvin and using the constants from the data sheet of the thermistor, and then we convert it to Celsius. So then we calculate the linear temperature model based on two known temperatures that we measured. We measured this ice pack with this thermometer, and that was -4 degrees, and then we measured the ambient air temperature, and that was 22 degrees. So then we made the linear model off those 2 points. And then we calculate the percent error by subtracting the Steinhart model value from the linear model and dividing that by the sum, and then multiplying it by 100, mostly just for the label. And then we update the percent error label on the figure. The next part of the code is where we get the points of the Steinhart model line, and we create an array of times and temperatures. And then we use the moving mean function from Matlab to calculate the moving mean based on 51 data points. And then we plot that as the average temperature line. So then down here at the very end, we're just adding the points to the figure with the animated lines and moving the x-axes.
Here we have our running temperature graph. You have the linear model in blue, the Steinhardt model in red, and the running average of the two in green. The temperature measured is in degrees Celsius, and you can see the thermistor resistance in the top left corner and the photocell resistance in the top right corner. I will heat up the thermistor now. You can see it climb. And note that they do intersect at 25 degrees Celsius, the linear model and the Steinhardt model. I will cool off the thermistor now. And you can see them intersect at 25 degrees Celsius again.
I think something that we could improve on next time would be taking the resistance of the photocell and changing it over to nit or to lux and creating that into a live graph so that we could see the brightness of the room or wherever.
Also, if we were to expand upon the project, we would 3D print an enclosure and display the temperature to an LCD screen, find a way to mount it to a window so we could look at the screen and figure out what temperature it is outside.
We could also build all the components on the Arduino and external components into one PCB.
And apart from that, I think our project went very well.